All right, let's get right into it. Welcome to this explainer, where we are going to completely decode the rather complex internal anatomy of multi-core current transformers, or CTs as we usually call them. Look, if you're working with modern power systems, truly understanding the exact behavior of these vital components is absolutely non-negotiable. So today, we're going to break down exactly how you can accurately protect and monitor million-dollar power infrastructure just by understanding the highly specific properties of secondary wiring, core materials, and saturation factors.
Okay, here is our roadmap for today. First, we'll touch on the modern engineer's reality. Second, we'll dive into the multi-core CT's concept itself. Third, we'll explore a really fascinating paradox: precision versus resilience. Fourth, we'll decode saturation and materials. And finally, number 5, we'll tie it all together with practical power system applications. Let's jump in.
Section 1. The Modern Engineer's Reality. Let's set the stage a bit, because today's power systems professionals have a massive amount of complex information to juggle on a daily basis. You know, modern engineers aren't just sitting in a vacuum doing math all day. The professional landscape changes incredibly fast. For example, our sources point out that you might literally be distracted trying to track recent changes to Canadian visitor visas converting to work permits, or maybe you're consulting abroad and having to navigate really strict anti-spam laws, where a simple cold email could result in a massive lawsuit. It's a huge cognitive load. But even with all of these completely unrelated legal frameworks pulling at your attention, your ultimate focus and your absolute zero margin for error always comes back to mastering highly technical systems like the multi-core current transformer.
Moving right along to Section 2, the multi-core CT concept. Let's leave the legal frameworks behind and transition back to electrical ones.
Think about the actual physical hardware of a multi-core CT for a second. It's brilliant. You've got a single primary winding, but it's inductively connected to multiple secondary iron cores. You could have 3, 4, or even 5 entirely different secondary cores, all sharing that one primary phase. They are all independently grounded, but here is the real secret sauce. They operate with completely unique behaviors. Why? Because the actual physical iron core material used for each individual secondary winding is fundamentally different.
And you can spot this immediately in the field. If you've ever stared at an equipment nameplate and seen strings of numbers like 100/5/5/5, well, each of those slashes and numbers perfectly decodes exactly how many separate secondary windings are packed inside that one single transformer housing. So in that first example, a 100 amp primary is feeding 3 totally separate 5 amp secondary windings. But it kind of begs the question, right? Why on earth do we need so many separate cores?
Well, that brings us to Section 3, the paradox of precision versus resilience. And this is a truly fascinating engineering hurdle. The different instruments attached to these separate secondary cores have completely opposing needs, especially when a dangerous power surge hits the grid. Measurement cores, like your class 0.2 or class 0.5 cores used for ammeters and energy billing, they actually need to fail, deliberately. We call it early saturation. If they don't tap out early, a massive surge will literally shatter the delicate billing meters attached to them. On the exact opposite side of the ring, you have protection cores, like class 5P10. These act as a rugged shield. They have to survive and stay perfectly accurate during those massive surges in order to trigger the safety relays. So, to protect those super-sensitive ammeters, engineers rely on something called the instrument security factor. They design the iron core so that it intentionally saturates at a low multiplier, usually around just 3 or 4 times the normal current. This ensures that the secondary current literally stops scaling up before it can fry your measuring coils. It's basically a carefully engineered bottleneck designed strictly for protection.
But think about what happens during a severe grid fault. The current surging through that primary wire can easily spike to 10 or even 20 times the normal limit. Boom! It's a catastrophic event. And while the measurement core is safely tapped out back at 3 times the normal current, that protection core is now facing a massive 20x surge that it absolutely must accurately capture and report to the safety relays.
Which leads us perfectly into Section 4, decoding saturation and materials. How do we actually manage a 20x surge?
To manage this, we have to look closely at the saturation factor. Unlike the measurement core that wants to tap out early, the saturation factor is the absolute ceiling of accuracy for a protection core. It dictates how far the current can spike before the magnetic core essentially becomes full and the secondary current behavior becomes dangerously abnormal. And remember, this upper limit is driven entirely by the physical properties of the specific iron core material used for that specific winding.
This brilliantly illustrates how we decode a standard protection specification string. Take 5P10, for instance. It's basically a code. The 5 guarantees a maximum 5% error margin. The P stands for protection class. And the 10? That is your crucial saturation factor, meaning this specific core will remain completely accurate while measuring a surge up to exactly 10 times the normal operating current.
But here is where your systems studies become absolutely vital. If your engineering studies calculate a potential fault on the grid of 20 times the normal current, you absolutely cannot use a 5P10 core. Actually, let me be stronger about that. It will fail. At 12 or 14 times normal current, a 5P10 core behaves abnormally, and your relay won't trip. You must upgrade and specify a 5P20 core so that the relay stays perfectly accurate at that extreme 20x limit. Okay, let's wrap this up with Section 5, Practical Power System Applications. We've talked a lot about the internal materials, but how does this actually look in the field? This breakdown maps out exactly how we match a core's engineered properties to its specific job. Starting at the top, you've got your highly precise Class Point 2 for revenue billing. Moving down, standard Class Point 5 for your everyday panel metering. Below that, the high saturation 5P10 cores for overcurrent relays. And finally, the PS class, a very special protection class reserved for differential and restricted earth fault, or REF, relays. One primary wire, up to 4 or 5 completely different cores doing entirely different jobs. It's like a giant puzzle perfectly fitting together.
Now, I really want to hammer home why that top row matters so much. If you have a basic low-voltage setup, you might only have 1 or 2 secondary cores because, frankly, the stakes are low. But when you're measuring power for a massive 132 kV industrial customer, you must use a highly precise Class 0.2 measuring core. Why? Because you are selling massive volumes of energy. We're talking millions of watts. Missing even a tiny fractional percentage of those megawatts because of an inaccurate CT core translates directly to a huge loss of money. In this business, precision literally equals revenue.
So, we have thoroughly decoded standard protection and measurement cores today. We know why one needs to saturate early to protect equipment and why the other has to push through the surge to trigger safety relays. But as we look ahead to that highly specialized PS class used for differential relays, a whole new dynamic enters the picture. So I want to leave you with this final provocative thought. When you're dealing with these special protection cores, what exactly happens when a core hits its mysterious key point voltage? It is a genuinely fascinating engineering hurdle, and honestly, it's exactly where you should focus your learning next. Thank you so much for joining me on this explainer, and keep questioning the systems around you.